Okay, so this is a short lesson on sets and Venn diagrams. Basically, what we're going to do is see and learn about the basics of sets, null sets, union of sets, disjoint sets, things like that. And then, on top of that, we're going to see how to represent these using Venn diagrams. Very useful for doing probability calculations. And so we'll see what Venn diagrams are, how we represent them, and what sort of problems we can solve with them. Okay, first of all, what is a set? Well, a set is a collection of distinct objects. The objects in a set are called elements, or we call them members. So what we'll see here is that, let's say we have set A. So we write it like this. We say there's set A, and we put equals, and we use the curly brackets like this to say, well, this is going to be a set. It's typically uppercase letter like this. So let's say that it just contains whole numbers, 1, 6, 4, 8, and 3. So that would be a set that contains those 5 digits. So these are the elements of the set. Elements of the set. Okay. So let's make another set. This could be set B, let's say. So set B is something different. It's got a carrot, it's got a pickle, and maybe a tomato. Okay, so this set contains 3 elements, or has 3 members, and in this case they represent vegetables. So this could be a set. So it's a set of these 3 vegetables. That's all a set is. That's all we really need to do at this point for that. You could represent things like, what is the number of elements in set A? And you've seen this notation before when we talked about the possible outcomes of events. So the number of elements in set A in this case, there are 1, 2, 3, 4, 5. 5 elements. Okay, and the number of elements in set B is, in this case, 3. So we read that as number of elements in set A. Okay, so that's good for now. We can move on to discussing some other things about sets. What else are sets? Well, there's something called a null set, and it's a set with no elements in it, and it's empty, and so it's called the null set or the empty set. You can represent it 2 ways. You could say that is a null set, or just empty curly brackets. It's a set that contains nothing. Okay, so it's like 0. It's just in set notation. All right, how can we relate sets to one another? Well, it turns out that there are ways that we can relate 2 different sets, or 3 or 4, or however many you want. And in this case, we're going to talk about what are called disjoint sets. And disjoint sets are things that have 2 sets or more that have nothing in common whatsoever. So for example, let's say we have set A, and set A contains 3 whole numbers, 1, 3, and 5. Okay. And set B also contains whole numbers of 6, 10, and 2. These 2 sets are disjoint, even though they both have the same number of elements, 3. They have no elements that are the same, so there's nothing in common with the 2 of them. There's no no elements in here that are the same. Or, we could do another one with our food option. So we could have the carrot, the pickle, and tomato. Could be a set with 3 elements in it. And set B could have in it lettuce and a cucumber. In this case, they are 2 sets, and they are disjoint because they have nothing in common. They have no common elements in them. Okay, so that's what disjoint sets are. So let's flip the sheet over, and let's talk about subsets. All right, these are the most interesting types, as you'll see in the work that we're going to be doing. So what is a subset? Well, it turns out that a subset if you see here, if all the elements of set B are also elements of set A, then B is a subset of A and is written as A subset B. You can see that little symbol there that says A subset B, saying B is contained in A or A contains B. So what we're going to do here, in fact, this is written incorrectly. This should be B is a subset of A. Okay, and you probably would have seen that when you were first doing this. So it's B is a subset of A, because I'm saying that all of the elements in set B are also elements of set A, but set A could have more elements in it. So for instance, if I make a set of whole numbers here and I say A is 1, 6, 4, 5, 10, so it has those digits in it, those numbers, and set B has 1, 5, and 10. This set has 1, 2, 3, 4, 5. Its size is 5. This one's size is 3. But you'll see that 1 is contained, 5 is contained, 10 is contained. So in this case here, B is a subset of A. Okay, and so that's important to know. Now let's say that we have C. Let's make another set, and let's call this set C, and it's going to just have the numbers 5 and 1 in it. Well, in this case, you will see that C is a subset of A, and C is also a subset of B. Now clearly, A is not a subset of B, and A is not a subset of C, because there are elements, it can't be that way around, right? You can't say that A is a subset of C. You say that C, because every element, all of the elements must be part of it. So you can't have it the other way around. So 5 and 1 are all of the elements of C are contained within A, so therefore C is a subset of A. Every set is a subset of itself. Okay, so that means, like, if you have A and it has 3 colors in it, let's say a blue, red, and green, A is a subset of A. I mean, it's self-explanatory that A contains itself, clearly. Okay, one more thing is that the null set is a subset of every set. Okay, so up here, if you have A is blue, red, green, then we can say that the null set is a subset of A. Okay, and that's just it by definition. The null set is a subset of every single set. Okay, equal sets. Well, sets are equal if they contain the exact same number of items and the exact same items. I think that's pretty self-explanatory. So let's say that we have set A, and it's just some digits again, just to make it easy. It's 3, 8, and 2. And let's say that B is 8, 2, and 3. Then B, A is equal to B. Set A is equal to set B. Okay? And it doesn't matter about the order. We'll talk about that later. The order of these elements doesn't matter inside the set. But these two sets would be identical. Okay, so we've learned about disjoint sets, subsets, equal sets, and what a set is. Now let's see how we can use what are called Venn diagrams to solve some problems and to just visualize the overlap of sets and what subsets are and things like that, just to give you a visual of how this works. All right, so if you want to analyze sets and do kind of set operations, then we can use Venn diagrams to help us do this. They're a very nice way of representing sets. Now we're only going to do 2 or 3 sets. We're not going to get into like crazy 4, 5, 6, 7 sets situations. So the first thing is, whenever you're making a Venn diagram, you start with the big box, which is called the universal set, S. Now the universal set contains all of the elements of the objects that are in question in set A and set B. Okay, so what we'll notice is that if I have a set A and a set B, then if there are items that involve whole numbers, let's say, like up here A and B, then in here what you'll notice is that this S, the universal set, is going to represent all whole numbers. So every whole number possible exists in this universal set, and in the subset might be just a small subset of these whole numbers. A might contain 3, 8, and 2, B might contain 10, 7, and 6, and maybe 3 is common, right? Okay, so what we're going to see is that the overlap of these things is really important. So what's happening here, also the union of these two things, and so we just must be aware of what's happening with this. Now, something you should know is that A is a subset of the universal set, and B must be a subset of the universal set. So if the universal set is all whole numbers, A and B must be subsets of that, and therefore contain whole numbers, but perhaps fewer of them or only select ones. Okay, so drawing these Venn diagrams is very simple. Make them big enough so you can actually put numbers in them and manipulate them as you need. So let's take a look at the different types of ways that Venn diagrams can overlap, or not overlap in some cases. So what we're going to talk about now is something called the union of a set and the intersection of a set. So let's say that we have the universal set S, okay, and we have set A, which is here, and set B, which is here. If I wanted to find out all of the elements that are in set A or set B, I want to look at this data here, or this information here. So what we call that is A union B. So we say it as A union B. The other way of writing this is OR. A or B, A union B. And we look at everything that's shaded here, the overlap, and the parts that don't overlap. Okay? It's upside down, or sorry, it's a U, as you see there. All right. What about just specifically right here, this little section? If I just care about this section here, what we call this here is A intersect B. Okay, so this is A intersect B, and the other thing we can say is AND. So A and B, or A intersect B, tells us just the overlap of the two sets. What's common between them? What is common between them? Okay, so we're going to see where the union comes into play when we're doing probabilities, and we're going to see where this intersection comes into play when we're also looking at solving problems related to this. And we'll be shading them in and kind of thinking about them in this way. So let's take a look at some examples, some different types of problems we can try, and see what we can do with it. Okay. So in your question sheet that you have, we're going to look at something called mutually exclusive and non-mutually exclusive events. and these relate very nicely to disjoint sets and the overlap of sets and things like that. So and we'll see how Venn diagrams can be used to help us solve some of these problems. So the first thing we're going to start with is this problem that you'll see here, which is at an event there's 18 shirts that are given away as a door prize. All right, Tobin wins the door prize of the night. There are 6 red shirts, 4 blue shirts, and 8 black shirts. So that makes 18. Tobin likes black and blue, but does not like red shirts. Calculate the probability that he will get a shirt he likes. Okay, so when we're solving these types of problems, we start out with the universal set, which is the set of all shirts. Okay, and Tobin likes what does it say here? He likes black and blue, but does not like red shirts. So if we look at the set of shirts that he does like, then we know that there are going to be 6 red shirts. Sorry, set A and set B. So let's say set A is the shirts that he does like. Then there are 8 black shirts and 4 blue shirts. And over here we have 6 red shirts. So in this case here, when we're looking at it, we say, well, what is the set of shirts that he likes and the set of shirts that he doesn't like? And they don't overlap because they're disjoint or they're mutually exclusive, right? He doesn't like either of them. And the universal set is a set of all shirts. Okay, so since there are 18 shirts, we would simply write that the probability that Tobin gets a shirt that he likes, or get a shirt he likes, is the probability of black or blue, like this. And what you'll notice is that we are talking about or, right? And because it's saying what's the probability that he'll get black or blue, because those are the 2 shirts that he likes the most. And so what we'll find out is, what is that probability? Well, let's figure out the number of black or union or blue. I like the word or, makes it easier to read, is simply the number of black shirts plus a number of blue shirts, like this. And we know that that is going to be 12 shirts that he likes. And the total number of shirts in this system is simply 18. So the probability that he gets a black or a blue is 12 over 18, 6 over 9, 2/3. So 2/3 probability that he'll get a shirt that he likes. The probability that he won't is only 1/3, and that's simply 1, subtract that. So the one thing we'll note is that whenever we're trying to find out the probability of 2 mutually exclusive events, or 2 things that don't relate to one another, that don't overlap, it's quite simple to figure out the number of, so we like the number of elements in A union B, that's this shaded area here, okay, is simply the number of elements in set A plus the number of elements in set B. And you add them together. We've already done this before, and you can see that we did it in this problem as well. Okay, so let's flip this sheet over and look at something when we have non-mutually exclusive events. And non-mutually exclusive events, these are different events that happen at the same time. So in this case, let's take a look at, it says 60 people were asked if they like dogs, cats, dogs, both, or neither. 20 people said they like cats, and 35 people said they like dogs, 15 like neither, 10 like both. Calculate the probability that a person selected at random likes cats or dogs. So The universal set is the set of cats and dogs, or sorry, people that like animals. And it says there were 60 people that were asked, and we basically are just trying to figure out, if we select them at random, what's the probability that they will like cats or dogs. So I'm going to make one of the sets C for cats and the other set D for dogs. Now what I'd like to do in these problems is typically start from the center and work your way outward from this. So if we look at this and we say, all right, it says that 15 like neither cats nor dogs. Oh, well, this is the set of people that like cats. This is the set of people that like dogs. It says 15 people did not like either. So we can stick them out there. There's 15 people in the universal set of people that are like that took the survey, and 15 don't like cats or dogs. 10 like both. Where's both? That's cats, that's dog. Oh, that's easy. That's both there, 10. Next part. So we've got 10 like both, 15 like neither. It says that 35 people said they like dogs. Okay, well here's dogs. Now you might be tempted to write 35 here, but you forget that some of those 35 people also liked cats. So the 35 people that like dogs, you know, and there's 10 that like both, that means that there's really 25 people that only like dogs, and 10 of those people of the 35 like dogs and cats. 20 people said they like cats. Well, 10 people only like cats, and 10 like cats and dogs. Now what we can see is that if we add all this up, we go 25, 30, 40, 50, 60. And it equals 60 people. So the number of elements in the sample set, or the universal set, is 60. And you check 10, 20, 30, 40, 5, 50, 60. It works. If you would put 35, 10, 25, or sorry, 20, 10, 35, 15, you'd have more people than there were actually being asked in this survey, and so therefore not correct. So now the question becomes, calculate the probability. So we know the total number of people is 60, so let's figure out how many people like cats or dogs. Okay, so you can write it like that, or you can write, you know, number is C or D. And when we look at that, this is the people who like cats or dogs. Okay, and so what we do is we add this up and we figure out how many people like cats and how many people like dogs. Well, there's 20 people, so we say number of people like cats plus the number of people that like dogs, like so. And if we do this, you say, oh, the number of people like cats is, that's easy, that's 20 plus 35, and you'd be tempted to say that there are 55 people that like cats or dogs, and you would be mistaken, because that's too many people, right? That would be 55 people out of the 60, but there's 15 that like neither, so we know we've done something wrong. And the thing we've done wrong here is that we've double counted this 10, right? You can see that we went 10 and 10 to get 20, 25 and 10 to get 35. So because we double counted, we have to subtract off the intersection of cats and dogs. So we subtract one of the 10s off. And so what we end up with is 55 minus 10 is 45. Now another way to do it is simply just count them up. 25, 35, 45. Bam. Should put a line here. And so following this procedure here, we say the number of elements in C union D is the number of elements in C plus the number of elements in D, subtract the intersection, because you double counted it. If there were 3, you would subtract off, you know, all the different intersections that happen. And you'll see how to do that a little bit later on. So now we see that the probability of cat and I'm going to write it like this now, or dog, cord, I guess it looks kind of weird, is equal to number in C or D divided by the universal set, all the people that were surveyed, and we get 45 over 60 is the probability. Uh, 6 times 5 is 30, so it's 12, divide by 3, 3/4. So 0.75, or 75% chance that a person randomly picked would like cats or dogs. So at the bottom here, for non-mutually exclusive events, that's events that have overlap. Whenever you're trying to find out the number of elements in A or B, it's the number of elements in A plus the number of elements in B, subtract off the intersection once. Or you simply use a Venn diagram and go add that, and that together, and that is the OR. If I asked for just the intersection, if I said how many people like cats and dogs, that would just be the 10 over 60. How many people liked only dogs? 25 over 60. And you can see how the diagram's super good and very easy to use to figure out that information. Okay, what we're going to do in the next video is we're going to go over a bunch of examples, and we'll solve these problems together, and we will see how to work through them, how to draw the diagrams. In a lot of cases I drew the diagrams for you, but we'll do that in the next video.